All right, let's take a look at the mathematics of Fulgora. Now the problem rises when you try to compute how many straps you need for the Fulgora science. Okay? One of the problem is a probability. Things are harder to predict, and then adding to that is quality. Right? You have 5 times as much of each thing. And before we start, I want to talk about some terms. So when you look at these all the probabilities and qualities, you will realize that things get complicated really fast. Okay, so you have a few terms we can deal with. One is called deterministic, in the sense that if I start with a certain initial condition, I can predict exactly what I will have in the future. Okay, so something like the recipe chain of the iron ore being converted to iron plate, being converted to iron gear. This is very deterministic, right? I can predict if 2 iron plates makes 1 gear and 1 iron ore makes 1 plate, I know exactly. I just multiply these numbers together and I conclude that I need 2 iron ore to get 1 gear. So this is relatively simple. And most of the things in Factorio would be this deterministic process, except for the things you see on Fulgora and the nuclear stuff. Okay, the other thing is probabilistic. Oh, I call it probabilistic. I think some statisticians might call it maybe stochastic. But well, for the words to be easier to understand, I would call it just probabilistic. This is things like strap recycling and quality, which involves probability, right? And usually probability problems are, well, the problem that we're dealing with is an optimization problem, right? We're trying to minimize the amount of straps you use to make science. We're trying to get the target number of science using the minimum amount of straps. And maybe you can even do legendary science. It's the same. Right? So it's an optimization problem, and usually optimization problems involving probabilities are solved using deterministic models. Right? For probability problems, you have this thing called average value or expected value, and if you treat everything using the expected value and pretend it's deterministic, usually that would give you a good model to solve the things. And in Factorio, a similar strategy could be used, but we'll see. It doesn't necessarily work. And when you try to figure out when it fails and when it doesn't work, you might come across this word called chaotic. The thing is, when you try to figure out this factorial problem, you will see that things get so complicated so fast, it's exponentially fast, that you feel like it should be chaotic, right? But the word chaotic actually has a very specific meaning in mathematics. Or, well, I don't want to just be pedantic with math words, but let me just strictly explain what chaotic means. Chaotic is a special case of deterministics. So if you're chaotic, you must be deterministic. That's a bit counterintuitive, because you would imagine, well, a naive understanding of chaotic means that there's no closed formula, right? No formula you can use to compute. The correct definition is that the idea is that chaotic is the idea of having a small change in the initial condition will yield a big change later on. That's what we call chaotic. So a classic example would be the double pendulum. If you have two pendulum connected to each other and you let it swing, it's chaotic. It's very difficult to predict what its trajectory would be, and a small change in the initial position would change how it moves drastically. But Factorio, I don't think the Fulgora science is a chaotic situation. I think it's a probabilistic situation, but with a high complexity. Meaning that it's hard to compute. And I believe that it is impossible to compute using today's technology. But a compromise would be you want to estimate. You can only estimate what you should get, and that's I believe is good enough for us, right? In real life. But just because it's high complexity doesn't mean it's chaotic. The point I'm making, I'm not just trying to be pedantic about these words. I'm not just saying, well, you thought it's chaotic, but it's really probabilistic. I'm not trying to be a show off that I understand the difference between these words. The point is that the fact that it's probabilistic means that in our case it's a linear problem. And being a linear problem, I do believe it can be modeled using a deterministic model. Again, I will describe the problem with buffers later. There is a problem with buffers, but I do think it's possible to compute. There's no formula for it, but it's possible to estimate using an Excel sheet, using a spreadsheet. Okay, and I think that's what they do in Factorio Lab or Factory Planner. If you go to Factorio Lab and you try to make, say, electromagnetic science, let's say I go on Fulgora and I use it's an upgraded machine. It tells me I should take 108.9 straps to make one electromagnetic science. Now this number, 108.9, is obtained using a linear model, using a deterministic model. It assumes that the probability of the recycling of these items are deterministic. You have fractional items. Now in application, you will not get fractional items. You will get whatever you get, the integer amount. And that might cause some problems, and I will explain later how it causes problem, how we fix it. But this number is given by a deterministic model, and it is in most cases it's good enough. It's good enough for us. And I myself have made a spreadsheet and have received the same estimate. So I think it's my guess is that it's using the same process as what I'm going to describe later in this video. But now if I try to make legendary Fulgora science, this is where the problem begins, because now I have to add select quality modules on all these machines and try to see how many straps I need, and try to see how many normal strap I need to make one legendary science. And this maybe it's probably just my own problem, but I don't know how to do the settings for this. The method I'm going to describe later will give you a sketch of how to compute this number. So let's see some examples. Okay. So the first example is simple. It's the deterministic example. So you have iron ore, 2 iron plate, 2 gears. And this one is, as I mentioned before, this one 1 to 1, and you have 2 to 1. So to make 1 gear, you need 2 iron ore. And suppose I'm using a furnace that says that I need, well, it's 1 gear per minute, per second, whatever unit you want to use, right? Let's say per second. Suppose I have a furnace that eats, say, 0.5 ore per second. Then to achieve this ratio, to achieve 1 gear per second, I must eat 2 ore per second, which means I need 4 furnace. Right? 2 over 0.5 is 4. I need 4 furnace for this factory. Okay, so that's what we're doing. We're computing the amount of things we need, then we're converting that to the amount of machines we need. Okay, that's basically the process of design. Well, if you do this for every single item in the factory, you would be. That's what all these Factorio lab and factory planner are doing. It gives you an estimate. Well, it gives you an amount of how many machines you need for each process. And well, something more complicated would be the oil refining, right? You have crude oil, which refines to light, and petroleum, and heavy. And well, you have one lower level refining, and you have an advanced refining, right? That gives you all 3. And then you have a tracking from heavy to light, and then a tracking from light to petrol. So this is a bit more complicated, and this is usually solved, well, the red recipe, the blue recipe, the green, and the yellow. Let's draw a table, right? If I have crude and crude, maybe heavy, light, and petrol. The red recipe would take, say, 100 crude and give me, say, 50 petrol. Okay, it's minus 100 crude for positive 50 petrol. And the advanced recipe, I'm just making numbers up here. It might be different in game. The advanced oil refining recipe might take 100 crude, make, say, 45 heavy, 35 light, and 20 crude, 20 petrol. Then the green one would take heavy, make some light. The yellow one take some light and make some petrol. Okay, so what we have drawn here is just a table of the amount of things you need. And if I want to set up, let's say if I do the first recipe 2 times, and I do the second recipe 1 time, I do the third recipe 3 times, I do the fourth recipe maybe 2 times again, then the input and output of the factory can be easily computed by just adding these numbers up, right? If I want to compute how much crude I'm using through this process, I would be taking 2 times minus 100 plus 1 times minus 100. It's equal to the amount of crude that I need. And for the heavy, I'm taking 1 times 45 plus 3 times minus 40. Apparently this is negative, so that means if I do apply this process, I would have a shortage of heavy, right? And more generally, we'll see if I want heavy to be 50, if I want to make 50 heavy and I want to compute how many crude I need, then I can't really set these numbers to anything I want, right? These numbers should be given by variables. If I make y0 times y1, y subscript 2, and y subscript 3, if I use these variables to calculate, I have y0 here, y1, then y1, and y2, and the other two formulas for light and petrol. I get four equations, where 3 of these should be my determinate value, like my target value. Like I want to make 50 heavy and 10 light and 100 petrol. I have to solve these 3 formulas to get y1, y2, y3, and y0. Then I use the result I computed to compute how much crude I really need. That's how you solve for this oil tracking process. And this, when you try to program it, or when you try to do it in a more efficient way, you will see the notion of matrix. What I have just written down here is called a matrix, right? A matrix of numbers. So the matrix is just the exact same exact same information as a bunch of equations. There is nothing fancy, really. And the only reason we're using matrices is because the theory of matrices are developed for a long time, and a lot of computer softwares they know exactly how to deal with matrices. So that's why, well, that's pretty much the only reason why we deal with them, at least in our applications. Okay, so, well, if you do compute this, you will probably find that there's no solution, no positive solution to get you these 3 numbers. Sometimes what you want to do is you say, I want to make at least 50 heavy, at least 10 light, and I want to make exactly 100 petrol. This might give you a solution. And to solve for these inequalities, it's usually these inequalities are more difficult to solve. And usually if you use the software to solve for these, you will usually only get an estimate. And the estimates, well, the programs can do estimates extremely accurately. So you don't have to worry about those errors. The errors are so small you would never have to worry about them. So let's see an example. Right? If I have, well, these equations here are inequalities or equalities with respect to some linear equations. So it's all linear. So maybe, well, if I have one equation that says that if I'm in the 2D plane and have one linear equation drawing this green line, and the inequality says that everything that's valid should be below this green line, and maybe everything that's valid should be above this yellow line. And my optimization problem says I should optimize the x value. I should maximize this value. Then this point would be my solution, right? This is the maximum for x that satisfy these green and yellow boundaries. Now the problem is that if you give it to, well, if you have more than 2, if you're in more than 2 dimensions, like here, we have 4 dimensions, or in general, you will have hundreds of variables, hundreds of dimensions. For a computer, it's more difficult to compute, and what they can do is you can do estimates. Like you start with any possible solution, and you move a bit to the down, you move a bit to the right, you move a bit down, until you reach a point that's close to the maximum, and you can compute what the error should be, and you can try to make the error as small as possible, and that I believe is how these programs are doing these estimates. Alright, so that's just a quick overview of how to do these computations using matrices, well, using writing down equations, but then equations are equivalent to using the matrix, and how to solve for these optimization problems. Next we have Fulgora. We have probabilistic problems, right? So let's consider a simplified version of Fulgora. If I start with the strap, it breaks down into items A and B at 50-50, and you combine A and B to make a science at a 1-to-1 ratio. I take one A and take one B to make a science. Now, how do we design this factory? Right? I can take a recycler and feed it strap, and from this I get 50% of it is item A, 50% of it is item B, and I feed this to a factory, an assembler that makes science. Now, because it's 50%, I would expect almost the same amount of A and B. But then the problem is that you're rolling a dice. It's in real life, you cannot get 0.5 of A and 0.5 of B. You can only get 1 A or 1 B. So if you get, so you have, say if I roll this dice twice, I could get AA at a chance of 25%, or AB or BA at a chance of 50%, and BB at a chance of 25%. Okay? If I get AB or BA, in this case, that's good. I can make a science out of it and continue. But in these two cases, if I have two A's, I'm missing a B. If I have two B's, I'm missing an A. So I cannot make science. I'm stuck with two A's or two B's. Right? So this is good. This is bad. Now, what can you do in this case? Well, before I tell you what you do in this case, let's see what's the problem here. The problem is that theoretically I get 50% A and 50% B, and everything should work out, right? For one science, this a theoretical computation would tell you that you need two strap. 50% of this would become one copy of A, and the other 50% of this two strap would become a copy of B, which gives you one science. That's the theoretical amount. But you will have a very big probability of encountering this situation of getting stuck if you do recycle two straps. Right? So you have two bad cases. And in these two bad cases, what you can do is you put extra in a buffer chest, and hope the next one that comes, let's say you get two A's, you put them in a buffer chest, and you hope the next one that comes is a B, right? So you have the recycler. You put A's in a buffer chest, you put B's in a buffer chest, and you have a factory that gives you science. If you have two A's, I can put them on hold in the buffer chest and hope that the next strap gives me a B and cancel out some A's to make it flow. Okay? Let's say my buffer chest has a size of 3. Well, I know buffer chests are usually much bigger. By the way, when I say buffer chest, if you hate chests as buffers, you also have belt buffer, right? Whatever buffer you have, buffer. So it could be a chest buffer or a belt buffer. And the idea is that if you have a base with a lot of belts, those belt buffer would be good enough so that you would never need chests as buffers. That's a big principle in Factorio that is really against chest buffers. But anyway, let's say I have a chest buffer of size 3. Okay, Then after 3 recycling of scraps, there's a chance of getting AAA at a 12.5%. That's still a big chance, right? And again, you're stuck, right? Because your buffer chests have filled up, and you have no Bs. Now what do you do? Yeah? Now some of you might say, well, 3 is too small, right? 3 is too small. If I set this buffer chest to be so large that the chance of getting so many A's, it's impossible. Well, it'd be nearly impossible to get 10,000 copies, 100,000 copies of A in a row, right? This possibility is astronomically small. So if I set my buffer to be bigger, there would be no problem. But that's not true. That's not true. Just how many A's you get in a row, right? This buffer chest is actually representing the difference between A and B. Right? If A minus B is positive 10,000, then I get stuck. Or if B minus A is bigger than 10,000, then I still get stuck. Right? The first case, the first box is full. In the second case, the second box is full. And if you are recycling the scrap, this difference, A minus B or B minus A, or maybe I write the absolute value of A minus B, the difference of this, as you recycle more and more scrap, this will grow. Or you have a probability of 1 as you run, as you scrap more and more things, that the difference will exceed 100,000. Oh, some people might say that you have this thing called the law of large numbers. The law of large numbers says that A divided by A plus B converges to 50%. So if I have if I do say 1 million scraps, right? If I recycle 1 million scrap, A over 1 million should be close to 50%. So maybe it's 51%, right? Maybe it's 50.1%, right? Let's say if it's 50.1%, I only have a 0.1% discrepancy. But the problem is that this 0.1% discrepancy out of 1 million is still a big number. It's still 1,000. And if you continue your factory and say you do 1 billion recycling, you get this, and you have 50.1%. You have this 0.1% discrepancy. Your discrepancy would be 1 million. That number would be so big it exceeds your capacity for your buffer. So this horrible situation that the buffer cannot hold will happen as time goes on. So what happens when your buffer gets full? You have to deal with it. And to deal with that, what you can do is, if it's full, you send everything, all the extra things, to a recycler and kill them off. It just evaporates all this stuff. They're just dead. You get rid of the overflow. Okay. But well, the fact is that you have to get rid of this overflow means that if you get rid of some overflow A, what if B catches up in a later situation? Right? What if B catches up later, and then you have too much B and you don't have enough A? If you have an overflow of A and you scrap it, you delete it, now you have less A than you were supposed to. So later, if B catches up, and then you would not have enough A to match it, right? And this will cause an overflow of B. and then you have to delete some b. And now you note that you have deleted both a and b, which could have been used to make science. Which means whatever you are doing here is not efficient. It's not the most efficient way of dealing with this. Right? So even though I computed the amount of scrap needed to be 2 scrap, because of this fact that I have to deal with this this overflow deletion, I'm not being efficient. So the perfect ratio is 2 scrap, but the real ratio is bigger than 2 scrap because of this unavoidable deletion of overflows. But how much bigger? Right? That's the thing that we need to compute. How much bigger? If it's bigger than 2, we know it's bigger than 2. If it turns out to be 20, that's not very. That means the 2 is really a really bad estimate, right? But if it turns out to be 2.0001, I would say that the 2 that we began with, it's still a good enough estimate, right? So how do we compute how much bigger than 2 this real consumption is? Okay, so again, it's a situation where we input scrap into a recycler, and we have a buffer for A, a buffer for B. Then we send them into a factory to make science. Maybe we call this buffer little a and little b, and then look at the difference between the two at each moment after each scrapping. Okay, so let's say I scrap 2 things. I might get AA, AB, BA, and BB. Then A minus B is 2 here, and 0 here, 0 here, and 2 here. Okay? Well, maybe I do even one more step. In the first case, if I start with A or start with B, the difference would be both 1. So you begin with 0. Okay? Beginning with 0, you have a 50% of chance, 50% chance to become 1, another 50 to become 1. Then you're working this way. From 1, you have a 50 chance of becoming 2, and 50 of becoming 0. Here you have 50% chance of becoming 0 and 50% chance of becoming 2. And from 2, you can go to 3 at a half chance, or go to 1. From 0, you go to 2. Oh, from 0, you can only go to 1, because you cannot go negative. Right? From 0, you can only go to 1. Then from 2, you can go to 1 or 3. And then again, from 1, you can either go to 2 or 0, etc. Okay? That's the behavior of this difference. And if A minus B is 0, that means you have the same amount of A and B. That means all of those can be safely made into science using this factory. The problem is that when you keep growing on this side, you can become 3, become 4, become 5, all the way to whatever buffer size is, right? If you grow, note that you can grow on this leftmost side or this rightmost side, or even in the middle. You can start with 1 here, then go to 2, then go to 3. So there's so many ways for this to blow up, right? There's so many possibilities for this to blow up. It's hard to compute, but again, it's a complex problem. Doesn't mean it's chaotic. This is called a random walk. A random walk. You're walking on the positive line. You're walking from 0. You have 50% chance to increase or decrease. Except when you're at 0, you can only go to the right. When you reach 1, you have a 50% chance of doing left or right. When you reach 2, you have 50% chance of doing left or right, and you keep walking. You keep doing this process of walking. This is called This is called a random walk, and it is a famous mathematical result that it's proven that if you just keep doing this random walk, you have a 100% chance that you will eventually reach whatever big number you propose. If I say a 1,000 and then keep walking randomly, you will have a 100% chance of eventually reaching 1,000. It doesn't tell you when. It might take 100 years or 1,000 years or whatever number of years, but you will reach 1,000. That means at one point, after recycling enough amount of scraps, you will have this difference being bigger than 1,000. And if your buffer size is 1,000, this will break, right? That's when you kill the overflow, right? You have two overflow lines. So what I've just said is that this dealing with overflow is inevitable, no matter how big you make your buffer size to be. So how often do we have to kill the overflow? As we mentioned before, killing the overflow, it's not efficient. It messes with your estimate of how many straps you need. Right? But if we can estimate how often we kill the overflow, we could estimate how much bigger our real ratio is compared to the perfect ratio. Okay? And this I have converted into a problem with random walk, and mathematicians have figured out, or maybe I should say statisticians, they have figured out how much it would be, how much it would cost. I'm not going to walk you through the proof of this, but I guess you just have to trust me. The science, the real required strap that you need per science is equal to 2 plus 1 over n, where this capital N is the size of your buffer. So if you have a buffer of size 1, you would need 3 straps per science. If your buffer size is 2, if your buffer size say 20, then you need 2.05 straps per science. Okay? So before we go into testing, let me just explain what happens on Fulgora. So instead of 2 items, you have maybe 20 items that you want to deal with. And with quality, you get maybe 100 items. And if you want to compute an exact value for the amount of straps you use, it's going to be extremely difficult because the number of cases you have to deal with is your buffer size to the power of 100. It's exponential. To calculate an exact amount for this would involve there is a formula for it, but it would be so large that nobody can ever express it. It doesn't mean it's chaotic. It's just complex. So it's so complex, the only way you can do is you can estimate it. You can do estimates on Excel or using a spreadsheet. Again, the idea is the same. You write down your item, maybe your item 1, and your item 2, etc., and with different qualities. So maybe I have item 1, but green, right? But with green quality, whatever. And you write down the matrix for the items and the recipes. So maybe you have recipe 1 that eats one copy of item 1 and returns a copy of item 2 or whatever, right? You have a matrix of all the recipes. You use this matrix, as we did before, to compute. Now, this matrix would be a determinate model, so whatever result you get is an ideal consumption for the scraps. Well, as we have explained, this does not match with the real consumption, right? which should be slightly bigger. But how much bigger? I would say that it's bigger, but well, let's say the ideal consumption is x. The real consumption should be x plus c over n, where n is your buffer size and c is a constant. Now, how do you determine this constant? Again, as I mentioned, it's so complex, there's no direct way to compute this constant. Well, there is a direct way, it's just we don't have, our computers are not fast enough to compute this. So what you do is you do estimate by simulation. Now, when I say simulation, it doesn't mean that you have to go into the game and build a factory like this and try to run the factory. Because if you can do that, why not just make it already? Right? For the simulation, what you use is probably you use some spreadsheet. I've heard that Office script, which is something with Excel that would allow you to do these simulations. Or another option is I think you can just do these simulations in Python, which I would believe is also pretty fast. And by the way, for this ideal consumption, even though you have ideal consumption, it's also just an estimation, as we mentioned, like where we're trying to solve for these polygons. Like in 2D, we have polygons, right? Defined by lines, whatever lines, right? And in 3D, we have polytopes. And in higher dimensional, we have polytopes. We have higher dimensional polytopes, and those are also complex enough that computers cannot directly deal with. So those are also computed by estimation. So even this ideal consumption is an estimate. And this, when you have Fulgora, when you have say 100 or 200, maybe for the recipes you maybe have 500 variables. 500, I would, from my experience, a computer should be able to solve something like this in seconds, do the estimates in seconds. I'm not sure if how long it takes for these simulations. I would expect them to not take so long. All right, so let's take a look at the case of batteries, which I will do a simulation in game later. The battery breaks into iron and copper with 50%, well, with 25% chance here. And I can rebuild the battery using 1 iron and 1 copper. I'm ignoring the sulfuric acid. That's irrelevant to me for now. I can rebuild the ideal ratio for battery, well, for how many battery ins, well, you would get 1 battery out per 4 batteries in, right? Because it's 25%. But the real ratio, this using the random walk method you can compute, happens to be 4 plus 2 over n. So 2 here is different from 1 over n as before. For the previous example, we had 1 over n. Now it's 2 over n. And in general, it's a constant c over n that you can only determine via simulations. And if I set n equals to say 2, then I need 5 batteries to make one new battery. If n is 10, I need 4.2. If n is 200, I need 4.01. Okay. So let's test this in game and see what we get. By the way, before we go to testing, you might have heard of a similar process of decomposing blues into red and green, and then remaking blue. But you could have a productivity bonus of 300%. And if you do this, that gives you an ideal ratio of 1 to 1. And some people claim that this means you get a free upgrade. You can freely upgrade the quality of blue circuits once you have this productivity. But as we discussed now, we realize that the real ratio is slightly above 1. So it's not really free. You would get stuck eventually and have to recycle, and the moment you recycle something, the moment you recycle an overflow, that will cause an inefficiency, and it's no longer free. Similar for this LDS thing, it's not completely free, I would say. Okay, so here's my simulation that I've built for this battery recycling. I've sped the footage up, but you can see for n equals 2, I have the ideal number, which is 4.0000, the theoretical number, which is 5.000, and the actual value that we're getting. You'll notice that the actual value is 4.7 something, which is slightly lower than what my theory suggests. And now similarly for the n equals 10, which predicts a 4.20, but we are only getting 4.17 or 4.18. And for n equals 200, I'm also getting something slightly lower. And I now have to explain why this contradicts my theory that I've spent so much time explaining to you. And I have a good guess, but I don't have complete proof for what I'm guessing. My guess is that I have set everything up so that I do have a genuine buffer chest of size 2, but I did not account for the hand of the inserters. So when the inserter holds an item and moves it from the chest to the machine, that also should be counted as a small buffer, as a small temporary buffer. And that means the true size of my buffer should be slightly above whatever I set to be. But for the mathematics, if the size of the buffer grows a bit, then I would expect the true value, the true amount of consumption to be lower than usual, to be lower than predicted. Anyway, thanks for watching, and as you can see, my theory is not completely perfect, but I hope this provides a better theory than just computing the ideal amount of consumption, which we do know is inaccurate.